Good day, everybody. I hope you're having a great day. Today we are going to be covering section 17.3, current and resistance. So this is additional to what we already did. We already did 17.1, where we did, hold on, let me open up. Everybody open up your book. We're going to be following along in your book on page, give me a second. Page 594. So we already covered electrical potential, remember potential difference, and we already covered capacitance. Today we're going to be furthering talking about electrical current and resistance. So the objectives of today's class are to describe the basic properties of electric current and solve problems relating current, charge, and time, to distinguish between the drift speed of a charge carrier, which is an electron, and the average speed of the electrons between collisions, to calculate resistance, current, and potential difference by using the definition of resistance, and to distinguish between ohmic, non-ohmic materials, and to learn what factors affect resistance. So first, let's look at the formula we're going to be using for electrical current, and then let's talk about what it is. So electrical current is the rate at which electric charges pass through a given area. So the electric charges pretty much are electrons. So how fast these electrons are going through a cross-sectional area of wire, if you want to think about it. A cross-sectional area of wire is a point in the wire, how fast the electrons are going. So if this is the wire, and this is a cross-sectional area, and the electrons are flowing through, how fast these charges are going through that cross-sectional area. So the formula for current is total charge passing through that area during a time interval divided by the time interval. So the units for charge, as we know, are the coulombs. For time are the seconds. So 1 coulomb per second is equal to 1 ampere. So the unit we're going to be using for current is the ampere. Let me do an example on electrical current. So the current in a light bulb is 0.835 amperes. So that right there is the current. Don't forget, current is, we're using the letter I for electrical current, which is weird. They don't use C because C is the unit for charge, which is Q, which is really confusing, but that's the way it is. So current is going to be I. How long does it take for the total charge? Charge is Q to pass through the filament of the bulb. So they're giving me the charge, they're giving me the current, and they want me to figure out the time. We're going to be using the formula. We're going to solve for T, so we're going to switch these two. So T is delta Q over I. We have delta Q, it's just plugging in I, and don't forget the unit for time is the second. Go ahead and do that problem. Pretty straightforward and just plugging in. So the math is really easy. Now conventional current, let's talk about what conventional current is. So what it was defined to be. So we know in order for us to have a current that we have to have a flow of charges. And the charges that flow are the electrons, which are the negative charges. So let's draw them. So imagine I have electrons flowing in that direction. So by definition, conventional current is the flow of positive charge. So electrons are negative. So if the electrons are flowing in this specific case in my wire to my right, my conventional current is going to be flowing in the opposite direction, which is the flow of positive charge, which is to my left in this specific example. So keep that in mind. Conventional current, even if the electrons are flowing, conventional current has the direction of the positive charge. So now let's talk about drift velocity. So in order for, if we have a wire and I have an electron here, drift velocity is the net velocity of a charge carrier moving in an electric field. So from point A to point B, that distance divided by how long it took for it to get there. And that would be the drift velocity. Drift speeds are relatively small because of the many collisions that occur when an electron moves through a conductor. So let's talk about what's going on. So imagine I have a light bulb down here and I connect it to a wire. There is a battery connected and there's a switch. Okay, so we know once it's open, this is my light bulb. If that is open right there, no current is flowing. Once I close it, automatically when you close it, if there is a battery source, let me draw the battery down here, then the electrons start to flow. However, the electron that is here or here is not going to be the electron that initially turns on, because once you close the switch, the light bulb immediately turns on. But the electron that was at the switch or that left the battery is not necessary. It's not going to be the electron that turned the light bulb on. When you turn the switch on, this electron and this electron, they start to flow, but they take a while to get to the light bulb. Okay? Remember, the metal or whatever, the metal that makes up the wire is made up of many electrons. It has many electrons inside of it. So the electron that's here starts flowing, but the ones that were already here, they also start flowing because of the change in the electric field. So whenever these start moving, every electron in the wire will start to move. So that's why it immediately turns on. However, for the electron that started here to get here, it takes a while because of the drift speed. If the electron were to move in a straight line, it would go much faster. However, it moves randomly, colliding with different particles. So it takes quite a while for it to get from point A to point B because it does not move in a straight line. It goes like that. So that's the reason why drift speeds are so slow. Now let's talk about resistance. Resistance is the ability of a material to oppose the movement of the electric current through that material. So pretty much it's how much it resists to the motion of the charges going through it. So you can think about it as friction. If there are particles wanting to move through a material and there's a lot of resistance involved or a lot of friction involved, these materials are going to warm up because of that. So first let's talk about how we're going to be finding resistance using the formula. The formula for resistance is delta V over I, which is potential difference, we know, divided by current. So let's go over the units. Potential difference, the unit for potential difference was the volt. The unit for electrical current is the ampere. And the unit for resistance is omega, which is the ohm. Okay? So we're going to be using that symbol for ohms, which is the SI unit for resistance. And now let's do an example. The resistance of a steam iron is 19 ohms. So they're automatically giving me R, straightforward. What is the current in the iron when it is connected across a potential difference? So they're giving me the potential difference, which is delta V, right there. And they want me to find the current, which is I. So I'm just going to be solving in the formula for I. So I equals delta V over R. And you just substitute, and you should get 6.39 because we're using, well, here they're only using 2 significant figures. I want you to stick to 3 significant figures, so 6.32 amperes. So now let's talk a little bit more about what resistance is. For many materials, resistance, or this resistance to motion of the charged particles, is constant over a range of potential differences. So these materials obey Ohm's law, which is the formula we just covered in that problem. Those are called ohmic materials. So for all the problems in your assignment, we're going to be talking about ohmic materials so that you can use Ohm's law. However, keep in mind that not all materials follow Ohm's law. For some materials, this resistance would be different depending on their temperature or their potential difference, etc. Sorry, depending on their potential difference, not their temperature. And these materials are called non-ohmic. We're not going to be covering those in our examples. You do need to know that they exist. So resistance, how much an object, or think about a piece of wire. A piece of wire, electricity goes through it, an electrical current goes through it. Every single wire is going to produce a specific resistance. That resistance depends on many different concepts, such as the length, the cross-sectional area, the temperature, and the material it is made of. For example, the length. Let's think about two wires made up of the same materials at the same temperature. One is short and one is long. When the current goes through them, which one is going to produce more resistance or more friction? Obviously, the one that has a longer length, because it takes more, because they're moving through a longer piece of that material. So even if the resistance was low, if it was twice as long, you would multiply it by 2, for example. So the longer wire is going to have a greater resistance. Now let's talk about cross-sectional area. That image didn't come out as I wanted it. So right here, what we're going to have is a wire with the same length but very thin. The cross-sectional area is also a factor involved in the resistance of a material. The larger the cross-sectional area, the less resistance. And the smaller or the thinner the wire, the smaller the cross-sectional area, the more resistance it creates. One very important concept is the material that the wires are made of. So here we have two wires of equal length, equal diameter, different materials. Materials such as copper offer low resistance. That is why copper is used to transport electrical current from one point to another if you don't want it to be used up, such as the wires out in the street in the posts, or the wire that is charging your computer at this specific moment. A lot of those are made up of copper because copper has a low resistance and it has a very low cost. So it's a very commonly used material. However, iron would never be material used to make up your wires, because iron is a high resistance material, which means that when an electrical current goes through it, it would warm up. So materials such as iron are used when you want to produce heat with an electrical current, such as in your stove or in your hair dryers or in the iron that you use to iron your clothes. So in those, if you have ever noticed inside of a hair dryer, whenever you plug it in and you turn it on, you kind of see a coiled wire that gets really, like, it starts glowing, red glowing when it gets hot. Or when you turn on the stove, what gets really warm is the coil. That's also called the stove resistance. Those are usually made up of iron because of its high resistance. Now, the fourth factor is temperature. If you have two wires made up of the exact same length, the exact same cross-sectional area, the exact same materials, but they were at different temperatures, the wire that has a higher temperature will produce a higher resistance. So just some basic concepts. So you want to go back, and before you do your assignment, you want to make sure you read pages 594 through 602 in your book. It's short reading, just some very basic paragraphs right there, mostly pictures. You want to read that because these are some of the main concepts from that reading. Resistors can be used to control the amount of current in a conductor. Salt water and perspiration lower the body's resistance. Just some basic concept like general facts. And potentiometers, which are devices found inside of everyday devices that allow the user to decide or change between different potential differences. To tap off different potential differences, it says here, you have a knob. So you have a knob that you're going to twist, and you're going to decide how much potential difference you want the device to have. They have very many applications. In fact, most of the knobs in everyday items, such as the volume and the control. So right now you don't have as many knobs because everything is more digital, but in the past there were a whole bunch of knobs, and knobs were made up of potentiometers. Joysticks in video games are also made up of, have here 2 different potentiometers, one for motion in the X direction and one for motion in the Y direction. So that's just an example of resistances, in this case potentiometers used in everyday life. So you want to do that reading, pretty interesting. Okay, once you're done with this video taking notes, then you can do your assignment. I'm going to be posting this video up along with your assignment, and it's going to be due on Tuesday. I hope everybody has a great day.